Morning, everybody. Welcome to today's expert webinar, Excitation Limits for Synchronous Machines. A couple of items before we begin. Today's presentation is being recorded and will be available for on-demand viewing using your registration login or on our Basler Electric YouTube channel. Handouts are available for participants in the handout section of this presentation. Please enter any questions into the questions section on the right side of your screen. Greg will answer any questions at the conclusion of this presentation. Any questions requiring follow-up will be answered by email. Be sure to follow Basler Electric on Facebook and LinkedIn to stay current with developments happening at our organization. Finally, future webinars are posted on the Basler.com events page. All webinars are free to attend, but registrations limited to 200 participants. Our resident expert, Greg Baker, has 20 years of experience in reviewing technical specifications, estimating costs to build, and writing proposals for excitation systems at Basler's Electric Company headquarters in Highland, Illinois. Prior to that position, Greg worked as a field service engineer for 4 years, where he commissioned excitation systems for synchronous machines, including limiter coordination. Prior technical work includes on-site technical assistance for digital energy management for commercial buildings and grocery store refrigeration controls. He has a Bachelor of Engineering degree from Southern Illinois University at Edwardsville. Take it away, Greg.
Hi, good day, bon dia, buenos dias, hudadak, bonjour. For the next half hour or so, we present an introduction to concepts for excitation for synchronous AC machines, with a specific interest in the excitation limiters used in the automatic excitation control systems. You will see the purposes for the limiters and associate them with the machine limits as documented by the manufacturers. Next slide. Electric machines include motors and generators. The electric motors accept electrical power and convert to mechanical motion. Large electric motors perform much of the heavy work to pump, to compress, to circulate, and to grind for processes on which our economy depends. The electric generators convert the power from prime movers to electrical power. These prime movers exploit kinetic energy that resides in waterfalls, boiling water, and the expansion from combustion of fuels as it converts to mechanical power. The electric machines are, in general, tied to each other by attachment to the bulk electrical system. The utility lines. When attached to the bulk electrical system, these machines share synchronized frequency and common voltage levels as transformed in the interfaces to the utility lines. Electrical machines are mechanisms with a rotating element and a static element. The rotor moves on its axle inside the stator of the machine. The rotation of the rotor is the means by which power is given by the machine or given to the machine. The stator is the interface with the electrical system. What makes the machine a synchronous machine is that the rotor imparts a spinning electromagnet that links the rotor through the rotating magnetic field to the alternating current in the stator. The electromagnet is energized by the current coursing through the magnetic windings of the rotor. The current is supplied by the exciter. The amount of current provided from the exciter is a variable that has critical importance to the operation of the synchronous electrical machine. Next slide, please. Synchronous machines differ from the induction motors and induction generators. The rotation of the rotors in induction machines are not synchronized with the AC current in the stator. The speeds are said to slip. The tally of AC induction motors dwarfs the number of synchronous machines. It is the large machines which will be built as synchronous motors or synchronous generators. The magnetic connection made between the rotor and stator establishes a strong link that will impart more of the mechanical torque. The stators, also known as armatures, of an induction motor, a wound rotor motor, or a synchronous motor are all the same. The difference is in the rotor. While the rotor is sufficiently excited, the machine remains locked in for all loads. Next slide, please. The characteristics of a synchronous machine are generally well documented, with data that we need to control the excitation. The machine builders provide documentations that pertain to the electrical and magnetic properties that we need to model the behavior of the particular machine. The AC machines were subjects of scientific exploration in the 1880s by scientists like Alfred Potier and Marie-Alfred Cornu, who developed many of the techniques and mathematical tools that are still in use today. As the machines became an industry at the end of the 19th and the turn of the 20th century, assisted by the works of Thomas Edison, Charles Steinmetz, and of George Westinghouse and Nikola Tesla, the establishment of conventions in service of communicating and documenting the essential parameters of these machines has led us to our ability to make good use of design characteristics and test results. A stranger to the field who begins his study may be flabbergasted by the assortment of values that make up a full data sheet. The convention, I promise you, is rather strong. Symbols and lowercase Greek letters used as variables in the established formulas are confined to really a small variety, the nature of which is also running with convention. The data does not become obsolete until the machine itself is modified. The documentation stands as useful to control designers and to technicians. A large AC machine is equipped with a nameplate, a monumentally permanent plaque with a convenient summary Next slide, please. Okay, again, a large AC machine is equipped with a nameplate. If you've seen a large machine's nameplate, you know it as a monumentally permanent plaque with a convenient summary of the characteristics of the machine. The machine nameplates are fireproof and very likely bulletproof. In our work to size a new excitation system for a client's existing machine, we make use of the nameplate, or at least a transcription of the values memorialized in the nameplate. Our concern with establishing excitation limiters draws our attention to machine's capability, its rated power factor, and its rated rotor current. See my stars on the slide that highlight those three things. The owner who is in possession of the machine's capability curves and commissioning report has a treasure that pays handsome dividends when controls are being retrofit. The capability curve of the synchronous machine tells the story of critical importance to controlling and protecting the machine from unsafe operation. Next slide, please. The thermal limits of the output of the generator or of the inputs to the motor are described on the real power and imaginary power, the PQ plane as you see here, as a circle, the radius of which is the machine's apparent power limit. This circle defines the first component of the capability curve. Next slide. Since the thermal limits of the machine depend on conditions of the cooling system, the radius of the limit circle will vary accordingly. These cooling conditions are not under control of the excitation control equipment, but they can be monitored for use in recalibrating limits that are based on thermal concerns. You can see the concentric circles in this diagram to derate for higher temperatures. Okay. Medium-sized and large steam turbine generators are cooled with hydrogen gas that is captive inside the sealed cover over the stator and the rotor. The hydrogen gas is cooled via heat exchangers that use either water or air to draw away the heat to outside the closed loop. The practical and conventional method is to scale estimates of the cooling capacity as proportional to the gauge pressure of the coolant gas. In this regard, the machine builders have provided documentation. Next slide, please. Smaller generators are cooled with air. Many in open loop with ambient air drawn in and exhaust air returned to the ambient air space. Some air-cooled systems provide secondary coolings with heat exchangers to draw heat away from the machine. The temperature of the coolant is a variable that influences the maximum capacity of the synchronous machine. Next slide. The key to the field current limit is the intersection of the rated rotor current and the rated power factor and the rated capacity. It's at the point in this diagram that I have marked with a 5-pointed star. The orange arc in my diagram here is the locus of that field current over the range of output operation of the prime mover. This arc forms a second component of the capability curve, the field current limit. Next slide, please. The purpose of the overexcitation limiter, OEL, is to ensure that the thermal capability of the rotor's field circuit windings is not exceeded, while the automatic voltage regulator is in control. The machine's nameplate will include a rating of the field current required at full load, rated frequency, rated voltage, and rated power factor. That value is fundamental for the purposes of establishing the limits for continuous field current for the machine. The machine builder's field current rating corresponds to the heat dissipated in the rotor windings, the built-in cooling support, and the physical limits of the insulation system for these conditions of the conductors. These limits are implicit in the nameplate rating with considerations for safety margins. You should expect to encounter overheating or heating approaching the thermal limits with prolonged operation with field current amplitudes above that rating. The input signal to the digital voltage regulator that is used to detect overexcitation is usually an output of an isolated field current transducer, which provides a small DC signal representing field current, or in some cases, a signal representing field voltage. The overexcitation limiter is dependent for its function on that input. The heating effects that raise the temperature of the field windings are proportional to the square of the field current. The action of the excitation system controls include limiting the continuous field current. The pickup point for the limiter is established from the limit based on what we find in review of the documentation. Take note of this slide's takeover limiter, which is the top of the two. And there's a curve built into one of the boxes. And the curve has an equation, T equals A over the quantity I sub F to the B power minus C in a box. We will visit this concept in the next slide. Next slide, please. The operation of the machine while operating connected to the bulk electrical systems will call for short time overloads, which will require levels of field current that exceed the continuous capacity limit. There are established standard short time thermal capabilities that machine builders observe in the design of the rotor, its windings, its cooling system, and the insulation systems. The basis of the short time capability is the relationship between the heating during the overload period and the machine's ability to absorb the heat without failure. The limiter picks up when the field current is sensed to be above the value configured as the limit. The action of the limiter is based on the amount of time and the difference between the limit value and the magnitude of the field current. The limiter includes a tolerance for short duration over excitation within well-established characteristic for the machine's capabilities. IEEE standard 421.5 provides guidance for setting these limiters. The field winding shall be capable of operating at 125% of rated load field current for at least 60 seconds. Starting from stabilized temperature at rated conditions, higher currents are permissible for shorter durations. For example, 209% rated load field current for 10 seconds. The relationship between the level of overexcitation and the time limit is normally characterized as inverse time functionality. That equation for the time, the numerator in that fraction, according to the standard, is 33.75, and the exponent for the current is 2. It's a square, remember, and the constant value in the binomial is 1. So it's I squared minus 1 dictates the amount of time that condition will be tolerated, or limiter will tolerate. The IEEE ANSI standard C50.13 field winding short time thermal capability curve should be used as a guideline for protecting the machine's field winding during short time overloads. The official scope of that standard addresses only round rotor, 2-pole and 4-pole machines. It is a reference in practice that applies even to salient pole machines. Again, more poles, slower rotation. Since the standards that specifically address them have not included this same guideline for rotor short time thermal limitations, the IEC equivalent also has no short time overload recommendations. Other portions of the field circuit, such as the excitation power source and the thyristor bridges, also have a thermal capability limit, a current rating, and need to be considered when applying overexcitation limiters and protection. A modern full-featured microprocessor-based digital excitation controller may include a feature that keeps track of the cool-down effects to shorten the OEL's delay time for a machine that has recently experienced an overexcitation event. There is some variation among limiters with respect to how the output signal is used. The limiter output may be used to lower the reference of the voltage regulator, or it may be a takeover limiter, which bypasses the voltage regulator and directly controls the level of excitation. Older excitation control systems may not have OEL or overexcitation protection, OEP, while most modern systems offer both, at least as an option. There are numerous variations on the design of OEL and OEP devices, but they all operate upon the same principles. Monitor the machine excitation level, allowing it to be raised above the determined level of the continuous field current for a short period of time, and reduce or remove excitation after that time is exceeded. The limiting action allows a machine to support stressed bulk electrical system as much as is practical without incurring thermal damage to the field winding. We must distinguish between an overexcitation limiter, again, OEL, and an overexcitation protection, OEP device. An OEL acts through the voltage regulator to reduce and maintain field current within the capability of the field winding. The OEP serves to remove the voltage regulator from service or to trip the generator offline when employed with an OEL. Properly coordinated, the OEP serves as a backup to the OEL to ensure that the OEL and OEP characteristics coordinate properly, or let's say they do not cross each other. Next slide, please. We proceed with an introduction to the synchronous machine that is operated underexcited, with an underexcited field, and the role of an underexcitation limiter, UEL. To begin with, to add to your armamentarium, a general understanding of why the machine connected to the bulk electrical system will run underexcited. So armed, we will describe the limiters in use with the automatic voltage regulators. Next slide, please. I would like to share a story of events which entangled a project in which I programmed the building's energy management control systems in the early 1990s. I will describe the source for the observed operating anomalies as a breakdown of the voltage control system to respond to loss of load. The site of the project was a large supermarket in Santo André, an industrial suburb of Sao Paulo in Brazil. I was part of a three-man team sent to address electrical issues at this site. My role in this project was to program the building's energy management system to strategically stage on controls to alleviate some of the stress on the emergency backup generators that had become frequently required in response to power outages. Before my arrival, the source of these power outages was not of interest to me, but that would change. The load staging strategy ran into trouble. The conductors to the loads had not been connected to the circuit breakers as had been assigned in the design of the power systems for the building. So the digital load control would have no benefit. The market's maintenance staff and we three engineers had to reconnect in an organized fashion the leads in the digitally controlled lighting panels, etc. We witnessed the event of a power outage while we were on site. The staff told us that once a week, the power would go off. Since this project dragged on for weeks, we observed that not only was the power going off once a week, but it was specifically going off on Saturday. Not just any time on Saturday, but it would go off at 5:00 p.m. on Saturday. One of the other two engineers in my team deduced the cause of the phenomenon. Within 10 kilometers of the supermarket is a rather large Volkswagen assembly plant in the nearby city of San Bernardo del Campo. The Volkswagen plant would shut down every Saturday at 5:00. When that plant shut down, they shut down all the machines and really dropped quite a bit of load off the line. My teammate learned that the same transmission line that feeds the power to our client's supermarket and the Volkswagen plant. At the time that the Volkswagen loads were all shut down, what caused the power to go off for my supermarket was that an overvoltage relay tripped the circuit breaker feeding the supermarket. This was not an outage caused by short circuit faults or open transmission line faults. The excursion of the line voltage above the tripping point following the shutdown of the VW plant set the local outage in motion. These two events were not simply coincidental. The rise in voltage, high enough to trip, was caused by insufficient dynamic response of the voltage control systems on the part of the utility. This event was caused by poor voltage regulation. The network did not properly respond to the disturbance of losing a large block of loads. Instead, poor control aggravated the event by triggering the drop of combined loads of the supermarket. If the voltage had been properly controlled, the protective relays would not have tripped the load off, which would have made all the difference in the world. So there are real advantages from the voltage regulation with good responses to changes in the load. And that comes from voltage regulators with high initial response, properly configured and set to hold the voltage within the acceptable range during loss of load. Next slide, please. The worst control operation for an underexcited synchronous machine is a reduction of field below the level required to maintain synchronism with the utility bus. Remember, what makes a machine a synchronous machine is the rotating magnetic field that links the stator to the rotor. This condition is commonly described as pull-out or out of step, device 78, to protective relay practitioners. The loss of field condition is similar and will, in most cases, result in the machine being tripped, disconnected from the utility bus. Operating underexcited is acceptable and sometimes required for stable grid operation. There are conditions of elevated voltage level that present urgent need for synchronous machine to absorb, to act as a load for the reactive power from the utility lines or the other parallel connected synchronous machines. There are conditions associated with underexcited synchronous machines that bear examination when establishing the underexcitation limiter. The capability curve for the machine includes a steady state stability curve, SSL. The trace of that SSL curve will most commonly intersect power, P. You see in our diagram here, we have two axes of P and a Q. The trace of the SSL curve will most commonly intersect power P axis of the graph at the point where the apparent power limit circle also intersects. You see there the orange arc. At the point where the apparent power circle also intersects. The shape of the SSL curve will rarely run as a continuous arc all the way to the reactive power Q axis. The operation of the machine at power level near the limit for cylindrical rotor machines present a thermal condition that menaces the stator's in-core with high eddy losses that are known to raise their temperature above tolerances. This phenomenon is less documented by suppliers. The testing for this condition is not standardized by century-old convention in the way the other characteristics we have discussed earlier are. The effect's intensity is affected by the geometry of the core and other parts of the machine, like the bearings for the axle. The documentation will, as regular practice, depict three curves for the underexcited operation limits based on these three limiting conditions: loss of synchronism, stability limit, SSL, and the in-core heating limit, often a partial arc. Again, that's active near the maximum power output. Next slide, please. The industry has relied on solid-state electronic analog control systems since they were invented. The underexcitation limiters and these analog controls are separate modules used to compensate the operation of the automatic voltage regulator. The concept essential for these UELs is that the underexcited pickup points are along a curved continuous locus in the underexcited portion of the PQ plane. To define the circle that traces the UEL arc, a center point is selected and a radius of that circle is selected. Experienced technicians and engineers develop techniques for finding the right settings for these parameters of the UEL. These techniques would be described as rule of thumb. The diagram shown here for a Westinghouse UEL for a WTA AVR is associated with instructions for the dial settings. These steps describe constants, such as the utility ties impedance, X sub E in this diagram, which are assumed values. The UEL's module settings are recommended to have added safety factor within the confines of the curve. Next slide, please. Digital excitation controllers include the UEL as integrated in the same hardware as the AVR. The variety of formats includes the takeover type and the summing type. For the takeover type of the UEL, the pickup of the UEL condition is seen as an output to auctioneering inputs, either the AVR or the UEL in control, that puts the AVR or the UEL in control of the field output of the exciter. The summing point acts as a compensator for the AVR's error detector. Next slide, please. The digital UEL has the flexibility to define a pickup curve that is not an arc of a circle. Users can base the path of this limit on more than one harmful condition of the machine. Next slide, please. The digital excitation controller is provided with configuring software tools for entering, editing, and documenting the settings that are loaded into the controller. The delays and gains apply to actions that are initiated by the pickup of the limiter based on running conditions. The values are in a format that allows conversion to corresponding values that are inputs to the modeling and simulation software. The most modern digital excitation controllers feature testing support with step functions and oscillography for commissioning and tuning, including the documentation of these test results. Sequence of events recorders assist in analysis of an incident after the machine has suffered it. Next slide, please. It is time to field your questions.
Thank you, Greg. We had a number of questions come in. Let me stop sharing my screen.
Excellent.
Here. All right. Let's see if I can get to them. Okay, one came in. When is it recommended to use OEL summing point mode or OEL takeover mode?
Okay. Either one is fine. It really is part of the architecture of the voltage regulator, and in many of the digital regulators, that's the way to go. Now we have both, in our digital excitation control products. The over excitation product as takeover has a more definite, immediate control of the field to limit it. If your voltage regulation is being run at the highest level of excitation all the time, you're always running overexcited, and you're running at the very margins of the protective curve, you probably want to have a takeover. But the summing point works too. As somebody setting it up, the thing you contend with, and you may not want to do this, is that the AVR is still in control for the summing point. So what happens is the AVR and the OEL do something we call bucking. They oppose each other, And so you have to make sure you tune the OEL to be aggressive enough to win that little bucking fight when it needs to be. Now, and there are some stability concerns about, two modes bucking each other, and if you're concerned about those stability issues, then perhaps the takeover is your favorite one there. I hope that makes sense to you, what I just said. The people who write the specs generally dictate this, but I don't really know what they're using necessarily. But if it were me, I would definitely want to use the takeover if I had, for instance, a PSS, a power system stabilizer, also in the machine. I hope that helps.
Great. We had a question come in. Could you repeat the name of the standard for OEL setting guidance, please? And I think someone
Yes.
asked it as 421.5.
It is.
Okay.
And the definition is also a formerly ANSI standard, now IEEE C50.13. And again, it is specifically indicated for cylindrical rotor machines, but the same sort of time value of overcurrent would apply. But yeah, the instructions about tuning, I guess, and modeling more about modeling is a 421.5.
Great. We had one other one came in, said, I also need information and standards of OEL.
Okay. I guess that's the same question.
Okay.
Did that answer that question?
Okay, great. Let's see. One more came in. 40 LOP protection should be coordinated with UEL. If so, what margin should be expected?
Okay. Yeah. You probably, it sounds like somebody who's run into the problem where the two limiters are both active at the same time. If you're using a digital excitation limiter, you have the ability, of course, to have takeover, but you could have cycling of limiters as one comes out of pickup and then the other one comes into pickup, and then that can cause oscillation. It's a real issue. So if you have an analog version, it is very difficult to remove that instability. What you have to do is you have to make sure that your pickup traces don't cross each other in the within the limits. Now we showed this curve and the output limits are that circle, but really the turbine or the prime mover power also is limited. So if your traces of your limiting pickups are beyond where the point where they meet, where they intersect, is beyond the prime mover's output level, then they won't actually cross each other during operation. So that's a real, and I assume that's what you're talking about. You don't want them both to be bucking each other and cycling.
Great. Okay, I think that was all the questions that we had come in. Okay, one more. When performing a PRC 19 coordination study, is it reasonable for, in parentheses, two companies performing the study on the same generator to have differing opinions of the limits? Oop, I just lost that question.
I wouldn't be surprised. And it's kind of that's where I would say that, there's a little bit of philosophy in play, and it's not I know there are quite a few papers written about this. So there are, if the company is more, the owner of the machine is more concerned about conserving the machine itself, they'll ask you to limit closer to unity power factory when you're under excited. If however the power pool is demanding support for voltage, you may have to open those limits up. Now, unfortunately, unless something has changed, I don't know that I've seen a really good case of empirically derived data about that as for the cylindrical rotor machines, where the end iron heating, there aren't generally convenient little curves like we like for those things, and these machines can experience harm. So it is possible that those clashes of philosophy could change the limiters, and by the same token, it would change your under excitation protection. And the trace outside of the again, we're talking about protective relaying. The curves they look at is circles of impedance, and how close you're operating to let's say the outside limit of that protective relay can vary by philosophy. So I would say yes. But the neat thing about PRC 019 studies, they usually have a lot of things to say about why they picked what they did.
Okay, we're getting a bunch more questions coming in. Let's take one more, and then I guess we'll answer the rest via email. Go ahead. If you have questions, go ahead and put them into the question section, and Greg can answer these a little bit later today via email. Last one comes in. Do you have any recommendations on testing UEL and OEL? Right now, I just overexcite and underexcite my machines and verify that the OEL activates, and then I'm able to return to steady state operation in AVR mode. Is there some more robust method?
Well, I think it's how daring you are, what you're going to put your machine through. A lot of times when we're checking the stability of a limiter, we'll actually change the pickup points to well within a safe range. You want to see how the different modes oppose each other during an event like that, and see whether you've got oscillations and stuff like that. So it sounds like if you feel, and if the owners of the machine feel lucky, you could actually run the machine into one of those limits and see what happens with your hand over the 86 button, I guess. Anyway, I don't want to make light of it, but I would say that would be the thing. And of course, there's modeling software that should be of immense help, that will sort of do your experiment without having the machine at risk.
Great. Thanks a bunch. Okay, great questions. Like I said, we'll go ahead. Any other questions that get put into the questions tab, we'll go ahead and answer those later today. Just want to let everybody know that I have put a PDF version of Greg's presentation in the handouts section. If you click on the apps button below, and there should be a section for handouts, you can download that. You'll be receiving an email in about 1 hour. This presentation will be on demand. You'll be able to view it later. We'll also put a copy on our YouTube channel early next week. Next week, we have a presentation. Denny Raymond's doing, I think, a small microgrids presentation. I'll make sure that information's in our LinkedIn and on our Facebook page. Feel free to sign up for that. Again, these presentations are always free, and the information's available for you to view on demand. And thank you so much for your time today, Greg. Great information, lots of good questions, and we'll connect up with you guys next week. Take care.
Thank you.